Assalamualaikum and hi everyone. Today our group, which is Expert Team 1, will be presenting on heat exchanger design. For this section, there are four main things we need to understand, which are heat duty, heat transfer media, temperature driving force, and pressure drop. So starting with heat duty, this refers to the amount of heat that needs to be transferred in a heat exchanger. It is determined based on the enthalpy change between the inlet and outlet stream. This is important because it helps us to estimate how much energy is needed and what size of heat exchanger is suitable for the process. So the equation is Q equal to mH out minus mH in, which shows that the heat transferred depend on the flow rate and also enthalpy difference. Next is heat transfer media, which refer to the medium used to transfer heat. If heat is removed, we usually use something like cooling water. If heat is applied, we usually use something like steam. So basically, the selection of heat transfer media is important because it affect the heat exchanger's performance and efficiency. Next, this table shows the common type of heat transfer media and their typical temperature range of application. So basically, this table is important because it helps us to choose the most suitable heating or cooling medium based on the required process temperature.
I will explain the concept of temperature driving force for heat transfer and pressure drop in heat exchanger. In process design, especially when using simulation software, we typically use two-sided heat exchanger model. This model assumes heat transfer rates on both sides is equal. The heat exchanger is insulated and the heat loss to the surrounding are negligible. For the equation, the fundamental equation used is Q equal to U A delta T M, where the Q is a heat transfer rate, U is overall heat transfer coefficient, A is heat transfer area, and delta T M is mean temperature, which is a driving force. This equation shows that the heat transfer depends not only the equipment design but also the temperature difference between the fluid. For the importance of a driving force, the heat transfer rate Q is usually calculated from energy balance. The overall heat transfer coefficient depends on a factor like exchanger geometry, fouling, and streams conditions, and also the flow pattern of the streams. So understanding the driving force is very important for efficient heat exchange design. Okay, for the flow pattern, it has three types, which is called current flow, counter current flow, and cross flow. The most efficient flow pattern is in heat exchanger is called counter current flow. In this setup, the hot and cold fluid flow in opposite direction. This creates a better temperature difference along the length of heat exchanger. At the two ends, we define N1, which is the hot inlet and cold outlet, and N2, which is a hot outlet and cold inlet. The smallest temperature difference within the stream is called the minimum temperature approach. For heuristic 26 is very important for the subtopics. The optimal minimum temperature approach depends on the temperature levels. For example, below ambience, use less than 10 Fahrenheit, and around ambient, up to 300 degree Fahrenheit, use around 20 Fahrenheit. For the high temperature, about 50 Fahrenheit. In furnace, it use 250 to 350 degree Fahrenheit above inlet stream. This value help engineer design efficient system. For the mode in boiling heat transfer, different temperature range produce different modes. Below 10 degree Fahrenheit, naturally convection dominates, but the heat transfer is slow. Between 20 Fahrenheit to 55 Fahrenheit, nuclear boiling occurs, which give very high heat transfer. Between 50 degree Fahrenheit and 100 degree Fahrenheit, transition region usually avoid. Above 100 Fahrenheit, film boiling occur and heat transfer become low again. So the best condition is a nuclear boiling. Finally, pressure drop is another important factor. So the typical value for the liquid is 5 to 9 psi, for the vapor about 3 psi, condensing and boiling stream about 1.5 psi, and furnace stream about 20 psi. Pressure drop must be evaluated on both shell and tube side. However, during early design stage, we usually use conservative estimates since detailed geometry is not yet available. For vertical exchanger, we'll also consider additional pressure effect due to the height. In conclusion, the temperature driving force and the pressure drop is a key factor in determining heat exchanger performance, and it must carefully balance with flow pattern, boiling mode, and pressure drop to achieve the optimal design.
Now let's move on to the equipment for heat exchange. So firstly, we have the double pipe heat exchangers, which consist of an inner straight pipe and supported with an outer straight pipe. So there's two types of flow for these heat exchangers. Firstly is parallel flow, where the inner pipe and outer pipe's fluid move in the same direction, and the other is counter flow, where the inner and outer pipes fluid flow in different direction. In a case where more heat transfer is needed, this hairpin unit will be used. And you can see that at the side here I listed some considerations for the modification of the inner pipe when the stream is at different conditions. So this is table 12.3 about steel pipe data, where you can use the values to calculate the flow and also the heat transfer inside the heat exchanger. Now let's move on to the second type of heat exchanger, which is the shell and tube. So there are multiple types of shell and tube heat exchangers. Let's start off with the basic terminology. So shell is the casing for all of the tubes inside the heat exchanger. So for instance, let's talk about the 1-2 fixed head heat exchanger. So for instance, you can see 1, 2, right? So 1 means the shell. So the fluid will go in and out of the heat exchanger one time. And then for two pass, it means the fluid inside the tube. So the tube, I assume it's here. So it will go in and out. So two times. So that's what it means by the shell and tube. And then after that we have baffles. So baffles is inside the shell. It's around the tubes, and the purpose is to direct the flow of the fluids for the maximum efficiency in the heat exchanger. And just now we have the fixed head heat exchanger, right? So fixed head means that two ends of the tube are connected to the ends of the shell. As for floating head, it means that one end of maybe the tube is connected here, but it's not connected to the other side. It's kind of floating. After that, we have U tube, so it's a U-shaped tube. Then this slide shows the tube spacing in the shell and tube heat exchanger and also their benefits. Then this is table 12.4, which is the heat exchanger tube data, where the values can be used to calculate the heat transfer coefficient. This heuristic 55 helps to determine which fluid is more suitable to be used in the tube side or the shell side. After that, we have air-cooled heat exchangers, which uses air for cooling and condensing liquid streams in the fin fan heat exchangers. So, how does this work? Firstly, the hot fluid will go into the inlet nozzle, the hot fluid inlet nozzle, into the stationary header. So here they will pass through the high fin tubes, where the fin tubes provide a large surface area for heat dissipation. So you can see there are two fans at the bottom of the heat exchangers. They will blow air up through the fins and allows the fluid to cool down. And then after the fluid cool down, it will exit through the hot fluid outlet nozzle. For the initial design of air-cooled heat exchangers, heuristic 56 is used.
So now I will continue with the compact heat exchangers. There are three types of compact heat exchangers. The first is the plate and frame exchangers. They use corrugated plates with high heat transfer coefficient. Its fouling is low and surfaces are readily clean. It's limited to 300 and 400 degree F due to gasket seals. It's suitable only for heating and cooling with no phase change. The second is the spiral plate exchangers. It provides true counter-current flow and is suitable for viscous, corrosive, fouling, and scaling fluids. And the third one is the plate fin exchangers. It achieves very high heat transfer surface area and it can handle multiple streams in a single unit. Next, we have furnaces. It used to heat, vaporize, and or react process streams at high temperatures and flow rate. A process fluid flows through tubes in the radiant section. Heat transfer in radiant section is predominantly by radiation, while the convection section recovers energy from combustion gases. And then the heat transfer in convection section is mainly by forced convection. The stack gas temperature must not fall below acid dew point. And then we have heuristic 57 for the furnaces. It provides the typical value for the heat fluxes, process liquid velocity, and the thermal efficiency. Now we continue with the temperature driving forces in shell and tube heat exchangers. So we have a general rate of heat transfer, the equation 12.2, and then we need the equation 12.3 for the mean temperature driving force. And the mean temperature driving force is based on the assumptions that the stream flows are at steady state, the stream flows are countercurrent or co-current to each other. The overall heat transfer coefficient is constant throughout the exchanger, and each stream undergoes only sensible enthalpy changes, heating or cooling with constant specific heat. And finally, the heat losses are negligible. This is the ideal heating and cooling curve for countercurrent flow and co-current flow. For multi-pass shell and tube exchangers, we need to use a correction factor Ft. The equation is as follows. And then we can obtain the new rate of heat transfer in multi-pass exchangers. This is the graph of temperature driving force correction factor for different multiple shell pass heat exchangers.
Moving on to overview of heat transfer coefficients. To size a heat exchanger, we first need to find the overall heat transfer coefficient U. Think of U as a measure of how easily heat moves through several barriers, the two fluid films, the pipe wall, and any dirt or fouling layers. Because pipes have different inner and outer surface areas, we usually calculate U based on the outer area, AO. This gives us a consistent baseline for determining the total heat transfer area needed for our project. As you can see, we use equation 12.8 and 12.9. We use a specific resistance equation to link the overall coefficient to individual factors. The calculation accounts for the outside fluid HO, the metal wall's conductivity KW, the inside fluid HI, and fouling factors RF. We also use logarithmic mean area for the wall thickness to ensure the cylindrical geometry of the tubes is accurately represented in our math. Now, in the early stages of a project, we often don't have all the data for a rigorous calculation. For preliminary design, we use industry standard estimates for U based on the specific service. Refer to table 12.5. As you can see in the table, these typical values already include a total dirt or fouling factor. This is critical because it gives a dirty U for design purposes, ensuring our equipment continues to meet heat duty requirements even after months of operation. For example, a water to gasoline exchanger typically operates with a U between 60 and 100 BTU. For convective heat transfer correlations, to get more precise, we look at the fluid regimes inside the tubes. While laminar flow can be predicted by theory, we generally prefer turbulent flow in heat exchangers because it significantly boosts our heat transfer coefficients. We use several key correlations depending on the fluid type. The Dietz-Bolte equation is our standard for general turbulent flow. If you are dealing with highly viscous liquids, we pivot to the Sider-Tate equation, which accounts for the large temperature gradients at the tube wall. For the highest level of accuracy across a wide range of Reynolds numbers, the Gilinski equation is our go-to tool. Pressure drop considerations. Efficiency isn't just about heat, it's also about power. Every exchanger comes with a pressure drop test. We calculate this using Darcy or Fanning friction factors to account for skin friction. As you can see, equation 12.18. Following heuristic 31, we aim for specific ranges, for example, 5 to 9 psi for liquids and about 3 psi for vapors. We also have to apply correction factors for multi-pass exchanges, where the fluid loses energy every time it reverses direction in the headers.
Moving on to turbulent flow in straight, smooth ducts, pipes, and tubes of circular cross-section, which is especially important in heat exchangers, such as double pipe and shell tube systems. In these systems, fluids flow through smooth circular tubes, and one of the key goals is to predict the convective heat transfer coefficient, denoted as HI. This coefficient helps us understand how efficiently heat is transferred between the fluid and the pipe wall when there is no phase change. For turbulent flow, which occurs when the Reynolds number is greater than 10,000, several empirical correlations are commonly used, as well as an additional advanced model. First is the Dittes-Boelter equation. It's used to calculate heat transfer for liquids and gases in fully developed flow. The equation applies when the Reynolds number is between 0.7 and 100. The properties are taken at average bulk flow conditions. It is important to note that the exponent n changes depending on whether the fluid is being heated or cooled. N is 0.4 when heated and N is 0.3 when for cooling. This equation is widely used for practical heat transfer calculations. Next is the Coleman equation. This equation is almost identical to the Dittes-Boelter equation, but is expressed in a J-factor form using the Stanton number. It also applies to both liquids and gases and is valid for parallel numbers up to about 160. An important feature is that fluid properties are evaluated at film temperature, which is midway between the wall and bulk fluid temperatures. The third correlation is the Cedar-Tate equation. Shown in equation 12.13, this equation is specifically developed for liquids, especially viscous liquids, where the viscosity at the wall and in the bulk can differ significantly. It is valid for very high parallel numbers and includes a correction factor involving the viscosity ratio. Here, the subscript W refers to the temperature at the wall. A more advanced model is the Gniewski equation, shown in equation 12.14 and 12.15. This correlation is more accurate and widely applicable compared to the previous one. It considers tube diameter to length ratio for 0 in a diameter over L less than 1, and is valid over a wide range of conditions, such as Reynolds number from 2,300 to 1 million, Prandtl number from 0.6 to 2,000. Another key advantage is that all fluid properties are evaluated at bulk conditions, making it convenient for calculations. It also incorporates the Darcy friction factor, which is related to the fanning friction factor by Fd equals to 4F. For viscous liquids, a correction factor is applied as shown in equation 12.16, and for gases being heated, a different correction factor is used where the temperature is expressed in absolute terms. Now, besides heat transfer, we must also consider pressure drop in the system. For isothermal flow without phase change, the pressure drop in a straight circular tube is calculated using the Darcy or Fanning equation. These equations account only for skin friction at the inner wall of the pipe, and the friction factor can be obtained from a Fanning friction factor chart. However, in real heat exchangers, additional effects must be considered. For non-isothermal flow in a multi-tube pass exchanger, the pressure drop is modified using equation 12.19. This includes correction factors such as Kp, which accounts for contraction, expansion, and flow reversal losses, and the number of tube passes. A reasonable number for Kp is typically 1.2.
So next we move to turbulent flow in the annular region between straight, smooth concentric pipe of circular cross-section. So in an annulus, we deal with two distinct boundary layers, which is a convex inner wall and a concave outer wall. This asymmetry fundamentally alter momentum transport. To account for this, we must move away the straight pipe diameters and utilize the hydraulic diameter, which is DH. So as we can see, DH is defined as D2 minus D1, where in our Darcy calculation for frictional pressure loss, the DH become our primary characteristic length. And for the heat transfer analysis, we utilize a comprehensive Gniewski correlation to determine the Nernst number. This formula is particularly robust because it incorporate for Darcy friction factor, but also include the critical correction term, which is, as we can see, 1 plus dH over L to the power of 2 over 3. This allows us to accurately account for the thermal entrance effect, where the heat transfer coefficient are significantly higher before the flow become fully developed. And finally, the convective efficiency differ across the inner and outer surface. We apply a specific geometric correction ratio. We define that the Nusselt number of the annulus relative to the standard tube is equal to 0.86 multiplied by diameter ratio, which is d1 over d2 to the power of negative 0.16. So by integrating this correction, we can achieve high precision prediction for both pressure drop and heat transfer in complex annular system. Now we move on to turbulent flow on shell side of the shell and tube heat exchanger. At the tube side, as we can see earlier, the mathematic is ideal mathematic calculation. But on the shell side, they have a challenge due to, as we can see, cross flow and parallel flow, buffer geometry, and also the black box limitation. Now let's look at a simple stream analysis. Historically, the heat exchanger was often treated as a black box, assuming a perfect uniform crossflow. However, according to the Bell Delaware method, so he introduced a realistic breakdown to the total shell side flow in 5 primary streams. So first, stream B, the main cross flow, which this is the fluid that actually follow the intended zigzag path across the tube bundle, driving the majority of our heat transfer. And next is stream A and stream E. Stream A consists of fluid leaking through a tiny clearance between the tube and buffer holes, and stream E is the fluid is bypass the bundle entirely by leaking through the gap between buffer edge and the inside of the shell wall. Finally is stream C and stream F. So stream C is the bundle to shell bypass, acting like a highway that allow fluid to easily slip through the another gap between the outermost tube and the shell. And stream F represent the fluid flowing through open partition lanes in multi-pass design. So understanding this distinct stream is critical because leakage and bypass flow contribute very little to heat exchange and significantly reduce overall efficiency. So moving on to the mathematical framework. For the flow of liquid or gas across the tube, the shell side pressure drop can be predicted using the modified Fanny equation. So the formula is shown in these slides. So a critical component of pressure drop equation or Fanny equation is F, the modified friction factor. So this is calculated by using the base formula F equal to V multiplied with DO times GS over nu B to the power of 0.15. But the coefficient V is highly dependent on the geometric layout. So if the geometric layout is triangular pitch or staggered, so you can use the equation on the left. Or uh, if the layout is a square pitch, we can use on the uh, right hand side formula. So as you can see in the both formula, you can see the XT and XL. So XT and XL represent the ratio of the transverse pitch and longitudinal pitch to the tube outside diameter. So these precise geometric parameters ensure that our friction factor accurately reflect the physical resistance created by the specific tube.
Finally, it is worth noting that while we often focus on turbulence-sensible heating, there are vast sets of correlation for more complex scenarios. This includes laminar flow inside or outside of various duct geometries and paths with longitudinal or very fins. Furthermore, specific correlation are required when dealing with phase change, specifically condensation and boiling, or the unique internal structures of compact heat exchanger. Well, these are too numerous to list here. They are essential for specialized design and can be found in comprehensive reference like Hewitt 1992. To start, it is important to understand that designing a shell and tube heat exchanger is not a straightforward calculation, but an iterative process. This is because the critical factors like heat transfer coefficients and pressure drops are dependent on geometric details such as tube layout, baffle spacing, and the number of passes, which are actually the unknowns we are trying to solve for. We begin with known inlet condition and at least one specified exit temperature to kick off the design cycle. The first phase involves making high-level decision. We must decide which fluid flows in the tubes versus the shell and select the appropriate utilities from standard tables. Initially, we assume a simple one shell pass, one tube pass countercurrent arrangement. A vital part of this step is performing an energy balance to determine the heat duty and ensuring our design does not violate the second law of thermodynamics. If the estimated surface area exceeds 8,000 square feet, we design for multiple exchangers in parallel to keep the units manageable. Once we have a preliminary area, we move into specific geometry. We typically aim for a tube side velocity of 4 feet per second, though the acceptable range is 1 to 10 feet per second. We then select standard tube size like a 3/4 inch outer diameter and calculate the required number of tubes and passes. Because our initial estimate for heat transfer and pressure drop were just guess, we must now use this specific geometry to recalculate those values. This loop continues, refining the designs until the results between iterations stay within a set tolerance. As you can imagine, performing this iteration by hand is incredibly tedious. That is why industry professionals rely on computer simulation. For instance, the Aspen Plus HeatX subroutine can calculate outlet condition and pressure drops for a known geometry. For even more detailed work, we use the PGSC suite, HeatRun for thermal rating and optimization, and AeroRun for air-cooled units, and TIMS for mechanical design and pressure vessel coding. This program effectively seeks the optimal geometry, balancing the smallest diameter and shortest length against allowable pressure drop.
Next, we will continue with the purchase cost of heat exchanger. The first heat exchanger is shell and tube heat exchanger. The diagram on the left side shows the base FOB purchase cost in terms of surface area. And this figure only applies to the carbon steel tubes with 3/4 or 1 inch outer diameter, 16 BWG, 20 feet long, on square or triangle pitch with shell side pressure up to 100 psig. For the other specification of tubes, we can refer the equation 16.43, which is Cp is equals to FPFM FLCB. And Fm is the material factor for various combination of tubes, where A is the surface area in feet square, and you can see the equation stated below here. Then the value of A and B can be referred from table 16.25. FL is the tube length correlation, as you can see in the diagram below. For the tube length of 8 feet, the FL is 1.25 and so on. And the FP is the shell side pressure. P is given in PSIG and applicable from 100 to 2000 PSIG. CB is the type of part in the tube where air representing the surface area in feet square. And given in text, the textbook are giving the 4 different types of tube, which are floating head, fixed head, U-tube, and kettle vaporizer. Next, we are going to the second type of heat exchanger, which are double pipe heat exchanger. Double pipe heat exchanger are often selected for surface areas less than 200 feet and as low as 2 feet. And the diagram given here is the CE cost index of 567 is for the carbon steel with pressure up to 600 psig. For the cases other than the stated before, we are going to use this formula CP is equal to FP FM times CB, where FM is 2.0 for outer pipe of carbon steel and inner pipe of stainless steel. And if both pipe are stainless steel, the value will be 3.0. The FP is the pressure factor. The P given is ranging from 600 to 3000 psig, and the CB is given as well, and the A is also the area in feet square. Next, we are moving on to fire heaters, which the standard tips are made of carbon steel for temperature up to 1100 Fahrenheit and pressure up to 500 psig. For CE equals to 567, the base cost for Q is from 10 to 500 million BTU per hour. And these are the given equation for the CB. And the CP given are also same with the previous example. FM is 1.4 for CR, MO alloy steel, and 1.7 for stainless steel. For the FP value, the range given for the pressure is from 500 to 3000 psig. These are the graphs that we can refer to when it is in the case of CE equals to 567 and pressure up to 500 psig.
Now I will explain exercise 12.5. So in this exercise, we're designing a shell and tube heat exchanger for a water-to-water process. Specifically, we need to cool 100,000 pounds per hour of hot water from 160 degree Fahrenheit down to 100 degree Fahrenheit using 200,000 pounds per hour of cold water entering at 90 degree Fahrenheit. So we need to determine the required heat transfer area and the resulting shell diameter using 20 feet copper tubes. So we start with the energy balance by looking at the cold water stream, which flows at 200,000 pounds per hour and heats up by 30 degree Fahrenheit. We calculate a total heat duty Q of 6 million BTU per hour. Next, we find the drying force. Since the hot water enters at 160 degree Fahrenheit and leaves at 100 degree Fahrenheit, we calculate the log mean temperature difference, or LMTD. So for this countercurrent setup, the LMTD is 21.65 degree Fahrenheit. Then we calculate the overall heat transfer coefficient, UO. Using the formula provided in the problem, we combine the internal and external film coefficient, Hi and Ho, with the thermal resistance of the copper tube wall. This gives us a UO of 88.65. So finally, using the heat transfer equation, A equals to Q over U times LMTD, we find that we need a total surface area of 3,126 square feet. So moving on to part B, first we determine the number of tubes, NT. A single 20-feet tube with a 0.75-inch diameter provides about 3.93 square feet of area. Dividing our total area by this value tells us that we need approximately 796 tubes. So to find the shell diameter ds, we use a standard design heuristic for tube on a 1-inch square pitch. The formula is ds equals to 1.2 times pitch times square root nt. So by inputting our values, 1.0 inch for the pitch and the square root of 796, we get a calculated diameter of 33.x inches. So in a real-world application, we will round this up to the nearest standard size, resulting in a 35-inch shell. Then I will explain for exercise 16.11. So in this exercise, we are estimating the bare module cost for a 1-2 shell and tube heat exchanger. We have been given the process temperatures, the heat capacity flow rate of the cold stream, and specific mechanical requirements, which are it must be stainless steel, handle 100 bar of pressure, and utilize a floating head design. First, we determine how much energy we are moving. Using the heat capacity flow rate of 40,000 BTU per hour degree Fahrenheit and the temperature change of the cold stream from 80 to 140 degrees, we calculate a total heat duty of 2.4 million BTU per hour. Next, we find the log mean temperature difference, or LMTD, based on our inlet and outlet temperatures, the LMTD is 18.2 degree Fahrenheit. To find the size, we need the overall heat transfer coefficient. Since both the tube side and shell side coefficient are 50, and assuming no fouling, our U value is 25. Dividing our duty by U and the LMTD gives us a required surface area of approximately 5,270 square feet. Moving from the technical requirements to the economic analysis, we apply Guthrie's method to determine the financial investment required for the equipment. We start by calculating the base cost CV for a standard carbon steel exchanger at a base pressure. Using the previously determined surface area in a power law correlation, the base cost is estimated at approximately 63,300. Because this specific exchanger is not a base model, we must adjust this figure using specific correction factors to account for the high performance requirements. So to handle a high pressure of 100 bar, we apply a pressure factor of 1.6, and to account for the stainless steel construction, we apply a material factor of 4.02. When these multipliers are applied to our base cost, the actual purchase cost of the unit jumps to 407,000. So in the final step, we calculate the bare module cost, which represent the total cost of the unit, including installation, piping, and instrumentation. So by applying the standard bare module factor of 3.17 from our reference tables and adjusting for inflation, scaling the cost from a CE index of 500 up to the current index of 505, we arrive at a final estimated project cost of 1.29 million.
For the Excel calculation, we need to have the unit conversion to standardize our units, and the length, area, and pressure of the tube will be converted to feet square and PSIG. The material of the tube and the shell is stainless steel and the type is U-tube. So for the FL tube length correction, our tube length is 7.87, which approximately same as the 8 feet, so we assume that our FL is 1.25. Based on the CEDA, all the formula is inserted into the Excel sheet, which is the FP, FM, and CV. For the FM, the small a and b is get from the table, which the material is stainless steel, small a is 2.7 and small b is 0.07. And we will multiply all of the four values to get the FOB purchase cost CP. And then we will times with the C letters divided by the C base to get the new FOB purchase cost. And the C letters is get from the Chemical Engineering Plant Cost Index.